this presentation, we will learn how to draw a Hasse diagram. So let's get started. By the end of this lecture, you would know what is a Hasse diagram and how it is useful, how to draw a Hasse diagram by following a predefined procedure, what is the easiest way to draw the Hasse diagram. These are all the things which we will discuss in this lecture. By the end of this lecture, you would know all these things. So without any further delay, let's get started. Let's say we have a set S which consists of these elements and relation R is defined on this set S. R is nothing but set of all ordered pairs A, B such that A divides B. Okay? We know that S, R is a poset, right? Because reflexive, antisymmetric and transitive properties are satisfied for relation R, right? Therefore, it is clear that S, R is a poset. You can see that reflexive property is satisfied because A divides A. Antisymmetric property is satisfied because if A divides B and B divides A, then obviously A is equal to B. There is only one way, right? And transitivity is also satisfied because if A divides B and B divides C, then A must divide C. As simple as that. Therefore, R is a partial order and S, R is a poset. Let's try to represent relation R, which consists of all ordered pairs A, B such that A divides B using a directed graph. This is what we want right now. We want to represent this relation R using a directed graph. This relation is defined on set S, which consists of 5 elements 1, 2, 4, 6, 8. Okay? Let's try to draw the directed graph for this relation. But before that, we must understand why do we need a graph. It is always easy to work with graphs, let me tell you. We can see the benefits of using a graph to represent a partial order in the upcoming lectures. Okay? So later you would be able to understand that why do we represent a partial order using a graph. Okay? Instead of listing down all the elements of a relation, it is better to represent relation using graph. Now we will try to draw a directed graph for this relation, which is defined on the set S. So I have randomly placed all these points of the graph. And you can see these points are nothing but the elements of set S. There are total 5 elements in set S. 1, 2, 4, 6 and 8. Right? Basically, these are the vertices of a graph. Each vertex is an element of set S. Apart from this, we know that relation R must consist of all these ordered pairs. You can verify this that this relation R is nothing but set of all ordered pairs A, B such that A divides B. You can verify this on your own, right? Now let's just try to draw a directed graph for this relation R. We know that 1 is related to 1, 2 is related to 2, 4 is related to 4, 6 is related to 6 and 8 is related to 8, right? This means that every element is related to itself because of reflexivity property, right? So here we can draw a loop from 1 to 1. This must be a self loop. And we can also draw a self loop from 2 to 2. Then we can draw an edge from 4 to 4, then 6 to 6, and finally 8 to 8, right? These are all the self loops which must be present in the directed graph because relation R is reflexive. Apart from this, we must draw an edge from 1 to 2 because 1 is related to 2, okay? So let's draw an edge from 1 to 2. It must be well noted that the arrow must point to this particular vertex because 1 is related to 2 and 2 is not related to 1. That's why I'm drawing a directed graph for relation R, okay? It must be well noted that this relation is an antisymmetric relation. If 1 is related to 2, then 2 must not be related to 1. That's why an edge must be drawn with an arrow where the arrow must point to the vertex 2. Fine? Now, we must draw an edge from 1 to 4, right? So let's draw an edge from 1 to 4. Okay, this is how it looks like. And the arrow must point to vertex 4. Apart from this, we must draw an edge from 1 to 6, 1 to 8, right? Then 2 to 4 because 2 divides 4, right? So there must be an edge from 2 to 4. Then we must have an edge from 2 to 6, then 2 to 8, and then we must have an edge from 4 to 8, right? So this is our relation R, which is represented using directed graph. Fine? Now, I would like to tell you one thing. We can remove self loops. This is my suggestion. Okay? Self loops are quite obvious and they must be present for all vertices. We know this, right? Because R is reflexive. So we can remove them to simplify the diagram. Right now the diagram is quite messy, right? There are so many edges in this graph. So obviously we can remove some obvious edges, right? These loops are obvious. We can remove them, right? Obviously we know that 1 is related to itself, 2 is related to itself, 4 is related to itself, 6 is related to itself, 8 is related to itself, because relation R is reflexive, right? There is no need to draw self loops in this case. That's why I have removed them. This is my suggestion. Second thing is, we can remove transitive edges. It is quite obvious that if A divides B and B divides C, then A divides C. There is no doubt about this. If 1 divides 2 and 2 divides 4, then it is obvious that 1 divides 4. This means if there is an edge from 1 to 2 and there is an edge from 2 to 4, then it is quite obvious that there must be an edge from 1 to 4. There is no need to draw this obvious edge, right? Therefore, there is no need to show the transitive edges in the directed graph to further simplify it, right? Obviously, our target is to simplify this directed graph. That's why I want to remove all those edges which are not required to be drawn. That's why I'm removing this edge from 1 to 4 as well, because this is a transitive edge, right? Let's try to remove all the transitive edges in this graph one by one. Here, first we will remove this edge, that is from 1 to 4, because 1 is related to 2 and 2 is related to 4. This is a transitive edge, so let's try to remove this. Then we must remove this edge from 1 to 6, right? Because 1 is related to 2 and 2 is related to 6, right? It is quite obvious that 1 is also related to 6, so we can remove this. After this, we can remove this edge. And then we can also remove this edge from 2 to 8, right? This edge is quite obvious because 2 is related to 4 and 4 is related to 8. Then obviously we can remove this edge from 2 to 8, which is not required in this case, right? This is the simplified version of the graph. Isn't it now compact enough? Isn't it now simple enough that we would be able to understand what exactly is going on in this graph, right? This is quite a simple looking graph. Apart from this, my suggestion is to remove arrows as well, because if we assume that all edges are pointing upwards, then there is no need to show the directions in the graph, right? You can see that all the edges are pointing upwards. If you see this carefully in this graph, all edges are pointing upwards, right? So we can safely remove these arrows because it is our assumption that all edges are pointing upwards. There is no edge which is pointing downwards. So it is clear that we can remove these arrows as well, right? So let's just remove them. So this is the simplest possible version of the graph. And let me tell you, this diagram is called the Hasse diagram. Okay. Now this diagram is used to represent partial order relations with sufficient information. It must be well noted that this diagram is full-fledged. This diagram is used to represent partial order relations very well with sufficient information, right? The Hasse diagram is named after the 20th century German mathematician Helmut Hasse. Okay, you can see his picture. Now we will see the procedure to draw the Hasse diagram. Step 1 is to start with the directed graph. It must be well noted that we must start with the directed graph. Okay. Then we must remove self loops. This is important. Then step 3 is to remove all transitive edges, right? And here is the procedure to remove all transitive edges. Check if A, B and B, C are in partial ordering. We must check if A, B and B, C are in partial ordering. If it is the case, then remove the edge between vertices A and C. We know that A is related to B and B is related to C, right? So there must be an edge between A and C because that would be a transitive edge. We must remove that edge, okay? If C, D, this ordered pair, belongs to the partial order, then remove the edge A, D and you can continue in this way, right? We know that A is related to B, B is related to C, C is related to D. Then there must also be an edge between A and D. We must remove that edge as well. This is also important, right? In this way, we can continue and remove all the transitive edges. Now let's see step 4. Arrange each edge so that its initial vertex is below its terminal vertex, okay? Initial vertex must be below its terminal vertex because all the edges must be drawn from bottom to top, okay? That's why we must arrange each edge so that its initial vertex is below its terminal vertex, okay? And finally, we must remove all the arrows of the directed graph. And that's it. This is the complete procedure to draw the Hasse diagram. Fine. Now let's see one example. Draw the Hess diagram representing the partial ordering R, which consists of all ordered pairs A, B such that A is less than or equal to B on set S, which consists of 4 elements 1, 2, 3 and 4. Let's draw the Hess diagram for this relation. The procedure is simple. Start with the directed graph, right? Let's draw the vertices in this plane. First put the vertex 1 and then vertex 2, then vertex 3 and vertex 4. It must be from bottom to top. You can see the order over here, right? I have placed 1 below because 1 is the least element in this set S, right? And the least element always depends on the relation which we are talking about. Here the relation is less than or equal to. We know that 1 is related to 2, 2 is related to 3, 3 is related to 4. So 1 is the least element here. This is the reason why I have placed 1 at the bottommost position, okay? So this is the order which I have followed. So in this way I have placed all the elements, right? After this, we know that 1 is related to 2. So we can draw an edge from 1 to 2. Then we know that 2 is related to 3. We can draw an edge from 2 to 3. It must be well noted that 1 is related to 2 and 2 is related to 3. Therefore, we can draw an edge from 1 to 3 as well. This is a transitive edge, right? After this, we know that 3 is related to 4. Therefore, we can draw an edge from 1 to 4. Also, we can draw an edge from 2 to 4. And that's it. This is our directed graph, right? Where every element is related to itself, right? And obviously, we must draw these self loops from 1 to 1, 2 to 2, 3 to 3 and 4 to 4, right? That's it. This is our directed graph, right? Now, the second step is to remove self loops. Okay, we must remove all these self loops. So this is how it looks like. Now we must remove all transitive edges. Now you can see that 1 is related to 2 and 2 is related to 3. And I have drawn an edge from 1 to 3. This is a transitive edge, right? So we can remove this. After this, we can remove this edge from 1 to 4 and then this edge from 2 to 4. It is simple, right? So in this way, we have removed all transitive edges, right? And these edges are mandatory to be drawn. These are not transitive edges, right? Finally, we must remove all arrows because we know that the direction is from bottom to top. Therefore, there is no need to mention these arrows, right? So let's just remove them. And this is our final result. Please note that R is nothing but set of all ordered pairs A, B such that A is less than or equal to B. And this relation is a special type of relation defined on set S, okay? Let me tell you why it is a special type of relation. R is a total order or linear order and the poset S, R is called a totally ordered set or chain. Okay, you can see a chain-like structure is formed over here. When a chain-like structure is formed, then the relation is said to be a total order or linear order. Okay, now what is so special about this relation? R is a total order because in set S, every two elements are comparable. See, every two element is comparable. Right? So you can see that this relation is a special type of relation where every two elements are related. Okay? So it's a special type of partial order which is a total order. Got it? That is why this relation is a special type of relation because every two elements are comparable. That is why I have said this relation is a special type of relation where every two elements are comparable. Or in other words, we can say every two elements are related. Right? Here 1 is related to 2, 2 is related to 3, 3 is related to 4. Obviously 2 is related to 4, 1 is related to 4, right? That is why this relation is called a total order or linear order. Fine. And this is nothing but a special type of partial order relation. In partial order, it is not mandatory that every two elements are comparable. That is why it is called a partial order. While this is a total order because every two elements are comparable. Okay. Now, there is an easy way to draw the Hess diagram, let me tell you. We know that we are available with set S and we are available with this relation R which consists of all ordered pairs A, B such that A is less than or equal to B. Let me show the easiest way to draw the Hess diagram for this relation. It must be well noted that there must be an edge from 1 to 2 because 1 is related to 2. So let me draw this edge from 1 to 2. And obviously there is no need to draw the arrow because we know that 1 is related to 2 and 2 is not related to 1, right? Apart from this, we can also draw an edge from 1 to 3. But there is a question. Shall we draw an edge from 2 to 3 or 1 to 3? In order to break this confusion, always choose the top element in the hierarchy. Okay? Always choose the top element. Here, an edge is drawn from 1 to 2, right? Now, we must check whether 2 is related to some other element or not. Here you know that 2 is related to 3, so let's draw an edge from 2 to 3. Okay? This is important. We must not draw the edge from 1 to 3 because 2 and 3 are related. In this way, we would be able to avoid all the transitive edges, right? After this, we must check whether 3 is related to some other element or not, because this is the topmost element in this hierarchy, right? So let's check whether 3 is related to 4 or not. Yes, 3 is related to 4, therefore we can draw an edge from 3 to 4. Isn't that simple? Obviously, we can draw an edge from 2 to 4, but this is redundant. There is no need to draw this edge. This is a transitive edge, right? That is why we must select the topmost element in the hierarchy and we must compare it with the other elements in the relation. Fine. If let's say 2 is not related to any element above it, then we will go one step down and we will compare this element with the rest of the elements. As simple as that. Let's say 2 is not related to 3 and 2 is also not related to 4. Then we will check whether 1 is related to 3 or whether 1 is related to 4. If 1 is related to 3, we'll draw an edge from 1 to 3. Else, if 1 is related to 4, then we will draw an edge from 1 to 4. Okay? This is the procedure which we can follow in order to draw the Hasse diagram. Okay? There is no need to start from the directed graph. Even there is no need to follow the complete procedure. Although I recommend that you should follow the procedure, but you can easily draw the Hasse diagram without any problem. Okay friends, this is it for now. Thank you for watching this presentation.